Good morning, everyone. Welcome back. Thank you for joining us. We're glad that you're here. I'm Steve.
And I'm Scott.
And together we're Backyard Musings, the Science and Technology channel.
Yeah, and today we're talking about a health issue, and it involves some of our favorite friends, or some mice testing, but yeah, health issue, and probably would affect, I would say, a good majority of the people.
Yeah, so looks promising.
Yeah. So
researchers have identified a small molecule compound that appears to counteract weight gain and metabolic damage in mice exposed to a long-term Western diet. That's funny, a Western diet. A drug candidate developed by researchers at the University of Texas Health Science Center at San Antonio kept mice from becoming obese even after long-term exposure to a sugar-rich, fat-heavy Western diet. So they're eating double quarter pounders with cheese.
Everything's bigger in Texas.
The treatment also protected the animals from liver damage linked to poor diet, including fatty buildup and tumor formation. Give it to us. Would you like to know more?
The work points to an unexpected target: magnesium movement inside mitochondria, the energy-producing structures found in cells. Quote, when we give this drug to the mice for a short time, they start losing weight. They all become slim. And this is according to Madesh Muniswamy, PhD.
You're making that up. That up.
That's his name, I guess. I may not be pronouncing it right, but I can spell it for you. A professor of medicine. I'm probably not spelling it right or sounding it right. A professor of medicine at the Joe R. and Teresa Lozano School or Long School of Medicine. I think we've talked about this school before.
Yeah.
Yeah.
And you'll remember that mitochondria is what binds the force together.
Oh, absolutely.
The findings were published in Cell Reports on April 8th, 2026. Muniswamy, not making that up, director of the Center for Mitochondrial Medicine at UT Health San Antonio, was the study's senior officer. The research also included scientists from the University of Pennsylvania and Cornell University.
Magnesium is essential for life. It helps regulate blood sugar and blood pressure, supports bone health, and participates in many chemical reactions that keep cells running. It is also the fourth most abundant cation. Is that cation?
What it says.
Okay, in the body, behind calcium, potassium, and sodium.
But inside mitochondria, the study suggests too much magnesium may act less like fuel and more like a brake. When magnesium enters mitochondria through a channel controlled by a gene called MRS2, it can slow the cell's ability to burn sugar and fat efficiently. Does that mean I need to stop taking magnesium pills?
Well, I don't know, but you just switched to magnesium, right? You just got off of...
well, I switched when I take it. I take it at night now.
Yeah, instead of taking your melatonin, you're taking magnesium citrate, right? Or citrate, is that what it is?
Yeah, well, and I stopped taking the fish oil. Stop that.
That too. Man, you just made a big reversal here. You put on your own brake.
I'm practicing what we preach.
Yeah. Okay, this is a quote. It puts the brake on. It just slows down. Says co-lead author Travis R. Madaris, a doctoral student in Muniswamy's lab. To test the idea, researchers removed the MRS2 gene in mice and fed them a Western diet for as long as 52 weeks. Well, that'd kill them right there. What are we talking about here? Mac and cheese.
Yeah, double quarter pounders.
Quarter pounder with
Coca-Cola.
cheese. Yeah, Diet Mountain Dew. It's going to kill them.
Yep.
And it fed them a diet for as long as 52 weeks. Normal mice gain weight and develop signs of metabolic disease. Well, there you go. Mice without MRS2 stayed lean, despite eating similar amounts of food, drinking similar amounts of water, and moving about as much as the other animals did. So they had them on a regimen. What do you call that? Exercise regimen.
Yeah, that wheel, the gerbil wheel.
Oh, those are hamsters. Do mice do that too? I didn't know mice did that.
Maybe they did it for this test. I don't know. We're just the messengers, folks.
Yeah.
Their metabolism also appeared more active. The mice were better able to use sugar and fat for energy, and their white fat began showing signs of browning, a shift toward a more energy-burning type of fat. The liver results were especially dramatic. In typical mice, the Western diet led to fatty liver changes, fibrosis, liver enlargement, and frequent liver tumors. Gee whiz. Those problems were largely absent in mice lacking MRS2.
So when you mention that wheel, I'm envisioning a mice fat camp where they got these guys lined up. They got to go to the
Get
wheel.
on the wheel.
They got to go eat the McDonald's. They got
If you want your food, get on the wheel.
their liver and is that adipose?
Adipose, yeah.
Adipose, which is I guess fat tissues, showed no evidence of fatty liver disease, condition closely tied to obesity, type 2 diabetes, and poor diet. The animals also maintained healthier blood glucose levels and avoided several signs of diet-induced metabolic syndrome.
The researchers found that reducing magnesium entry into mitochondria changed how cells handled citrate, a molecule used to make fat. And my pill is magnesium citrate. So I'm starting to rethink. With less mitochondrial magnesium, less citrate appeared to leave the mitochondria for fat production. That shift may help explain why the mice accumulated less fat in the liver and body.
The team then tested a compound called CPACC, which blocks magnesium transport through the same mitochondrial pathway. UT Health San Antonio has filed a patent application for the drug. In experiments, CPACC reduced lipid buildup in liver cells, increased mitochondrial respiration, lowered plasma citrate, and promoted features of beige fat, a more metabolically active form of fat. In mice on a high-fat diet, injections of CPACC every 3 days for 6 weeks limited weight gain and improved a marker of liver function. So watch out, GLP-1.
Give it to me, man. I'll go on a trial test for the CPACC. I might try and contact that health, UT San Antonio Health, and see if they'll let me
raise your hand, right? Say,
raise my hand.
I'll do
what
it.
What I got to lose? Liver failure?
Yeah.
Huh. Medeiros said the collaboration was essential to developing the compound. Joseph A. Bauer, PhD of the University of Pennsylvania, and Justin J. Watson, PhD of Cornell University, were among the contributors. Quote, "We came up with the small molecule and Justin synthesized it," Medeiros said.
Justin.
The doctor.
Okay. The results.
Dr. Justin Wilson.
Yep. The results suggest that mitochondrial magnesium channels may be a promising target for obesity, fatty liver disease, type 2 diabetes, and other cardiometabolic conditions. Still, the findings are early. The main experiments were done in mice, and the study used a global MRS2 knockout, which means the researchers could not isolate the role of the channel in each individual tissue. The authors also note that future work will need safer, more refined MRS2 modulators suitable for human studies. Why not? Why?
Because they don't want you dying.
Well, but you're going to die anyway if you got any of those diseases, right? I mean,
they don't want you dying immediately. They want you to pass the test so they can market it and sell it and make money.
I guess. Sign that waiver, man. Get some humans in this thing. Okay.
Related studies published after the CPACC work suggest that mitochondrial magnesium transport may matter beyond obesity and fatty liver disease. In a 2024 mitochondrion study, researchers showed that lower magnesium levels inside mitochondria increase activity of the mitochondrial calcium uniporter, MCU, which controls calcium uptake into mitochondria. The finding helps explain how mitochondrial magnesium can influence calcium signaling, energy production, and cell stress.
In 2026, a hypertension study connected MRS2 to pulmonary arterial hypertension, or PAH. In diseased pulmonary artery cells, excess mitochondrial magnesium helped drive metabolic dysfunction, lactate buildup, calcium overload, mitochondrial damage, and abnormal cell growth. None of those. I have no idea what they are, but they all don't sound good.
They sound bad.
Yeah. Reducing MRS2 activity, improved mitochondrial function, and eased vascular remodeling in rats. I'm surprised they were able to use that MRS2. That just MRS.
It's a gene. It's a gene.
Yeah.
The CPACC is what blocked it, which is, I'm thinking having second thoughts about magnesium citrate now. I mean, if this is what it does to cells, can't be good.
Counterintuitive. I don't know.
I think I'm going to stop taking it, Scott, just to be safe.
Okay, well, let us know how that goes.
All right, folks, thanks for joining us. We'll catch you in the afternoon.
Take care, everyone. Have a good morning. Thanks.